First of all, I would like to thank the organizers of this nice workshop and for giving us the possibility to see each other and to discuss recent results via Zoom. Yeah, I will speak about possibilities to handle multi-objective optimization problems with constraints, and this is a joint work together with Christiane Tammer. Yeah, here you can see the topics of my talk. In the first part, I will give motivation for our studies. And in the second part, I will introduce the multi-objective optimization problems that we will study. In the third part, I will speak about the relationships between an unconstrained, this one, an unconstrained and constrained optimization problem. We will see that it is possible to generate the whole solution set of the constrained optimization problem by solving two unconstrained optimization problems. Yes, this is in part 4. And then I will speak about some applications in locational analysis, and furthermore, using the results from section 4, I will derive necessary optimality conditions, and finally, I will give some conclusions. Yeah, let us start with motivation. We consider a multi-objective location problem where M existing facilities, A1 to AM, are given, and we are looking for a new facility X such that the distances between the existing facilities and the new facility are minimal in a certain sense. The distances are given here in this example by the Euclidean norm. This is the Euclidean norm, and this is the formulation of the multi-objective location problem where the Euclidean norm, this one, is involved in each component. So we study here a multi-objective optimization problem because we have M objective functions. This means that the objective function takes the values in the M-dimensional Euclidean space. And so we are looking for Pareto efficient solutions with respect to the natural ordering cone in the M-dimensional Euclidean space. I will introduce this solution concept on the next slide. We suppose that the feasible set is non-empty and closed. So concerning the solution concept that we are using in the location problem here is given here in this formula. We are looking for Pareto efficient elements, such points X, for that these conditions here are fulfilled. So with other words, we are looking for elements, Pareto efficient elements, for that this intersection here is empty. This is a classical solution concept in multi-objective optimization that we will use for this example here. And now we consider the simplest example with only two existing facilities, A1 and A2. And we are looking for the set of Pareto efficient elements of the corresponding multi-objective location problem with two objective functions. Is X a Pareto efficient solution? No, it is not the case. As you can see here, especially X prime has better objective function values. And here in this figure, you can see in green color the whole set of efficient Pareto efficient solutions of this multi-objective location problem. If we would consider one more existing facility, A3, then we have here this multi-objective location problem with 3 objective functions, and then we can compute the whole solution set is the convex Hall of the existing facilities. This is only true for the case of the Euclidean norm in the formulation of the location problem. So, and for this simple location problem, multi-objective, where the Euclidean norm is involved, and under the assumption that the feasible Z, the non-empty closed and convex set here, Nguyen and Michelot derived this approach to compute the whole set of Pareto efficient solutions of the constraint problem by using the set of Pareto efficient solutions of the unconstrained problem. And furthermore, one has to use a projection of this solution set onto X using the Euclidean norm. And this can be described here also using the convex Hall, as we have seen before. Yeah, and this property here in the paper by Nguyen and Michelot is called projection property. However, here are some strong assumptions: convexity of X, and this projection property is only true for the Euclidean norm in the formulation of the location problem, but not for other more general norms, especially for the Manhattan norm or the maximum norm. This result is not true. Yeah, however, the authors have shown it for the Euclidean norm. The aim of this talk is to consider more general problems, also location problems with other norms, and also general multi-objective optimization problems, where the feasible set is not necessarily convex. So, coming back to the approach by Michelot and Nguyen, you can see here the problem. The feasible set is X. The set of Pareto efficient elements of the unconstrained problem is a convex Hall of the existing facilities. And using the projection property in this paper, you can see here the whole solution set in green color of the location problem, where the Euclidean norm is involved with a convex feasible set. So this is a known result from the literature, and we will derive more general results without convexity assumptions concerning X, and for more general multi-objective optimization problems. Especially, we will also consider problems where the feasible set is not convex. Here you can see again existing facilities for a location problem, and in red color, this is a forbidden region. This means a non-convex feasible set. Also for this case, here we have two forbidden regions, and the feasible set is outside of the red regions, such that we arrive at a non-convex location problem. And the element X prime that we computed before is now not feasible. It doesn't belong to the feasible set capital X. So the general formulation of our problem is given here. We have M objective functions. We are using the concept of Pareto efficiency. We suppose that the feasible set X is closed. And then here we repeat the solution concept of Pareto efficient elements for this general objective function. And furthermore, we are speaking about weakly Pareto efficient solutions if we replace the natural ordering cone in the m-dimensional Euclidean space by the interior of this cone. So for our approach, it is important to deal with lower level sets of real valued function h here, the level z, this is this one, and the strict lower level z. Here you can see the definitions, and it is easy to see that we have this relation if we are using a subset of Rn or the whole space Rn. So, and the objective function is given here by this vector. And for an element x0 belonging to X, we introduce these sets here. The first one is the intersection of the lower level sets of the function fi with a level fi at x0. The same for the level line and the strict lower level z. So, and then we have important result, I think derived by Stefan Nickel and also mentioned in the book by Matthias Ergot. We can give a necessary and sufficient condition for the properties that x0 belongs to the set of efficient elements of the constraint multi-objective optimization problem. This is the case if and only if this inclusion holds. And furthermore, x0 belongs to the set of weakly efficient elements if and only if this set with respect to the strict lower level set is empty. So as a conclusion, we get here that this intersection is a subset of the set of Pareto efficient elements of the constraint optimization problem. So, sorry, I have a problem to move to the next slide. Maybe no. Oh, sorry. Yeah, this was the last slide here. So, and our main question here for the talk is it possible to use methods well known from unconstrained optimization for solving unconstrained multi-objective optimization problems? Our results are included in several papers, and I will come back to these results in the talk. In order to formulate the assumptions of certain assertions, we need some properties, well-known convexity, quasi-convexity, and semi-strictly quasi-convexity. These are well-known properties, and using this assumption that the objective function of the multi-objective optimization problem is component by strictly semi-strictly quasi-convex, then we have this inclusion where we have here in this term the unconstrained problem and here the constrained problem. And furthermore, under the same assumptions, like in proposition 5, we have this assertion concerning the solution set of Pareto efficient elements of the constraint optimization problem. Here on the left-hand side and the right-hand side, we have sets of efficient elements of the unconstrained problems. So, and in order to formulate our main result, we introduce a penalization function. We add additionally to the given objective functions f1 to fm another objective function with a so-called penalization function. And for our assertions, we have to suppose that A1 and A2 are fulfilled for elements x prime belonging to the boundary of the feasible set x. We suppose that for the penalization function, the lower level z with the level phi of x prime coincides with the feasible set x, and furthermore, the level line of the penalization function with the level z phi of x prime coincides with the boundary of x. Yeah, at the beginning in our papers, we suppose the convexity of x, but we recognize that it is not necessary to suppose convexity. We replaced convexity by the assumptions A1 and A2. So, of course, one has to ask for penalization functions such that A1 and A2 are fulfilled. One is here the Minkowski gauge with respect to ZB that is here involved. Then it is easy to see that A1 and A2 are fulfilled under the convexity assumption concerning X. If X is not convex, like in the second case, we have here Rn without the interior of D. Such a construction is of interest in location theory with forbidden region. We consider convex sets D, but the feasible set X is Rn without the interior of D. Then we can use again the Minkowski gauge, but here in this form, the penalization function phi is defined. Again, with this ZB in the definition of the Minkowski gauge. So another example where assumptions A1 and A2 are fulfilled is the well-known Hiriart-Urruti function, oriented distance function, defined using the classical distance function here in this way. And it is easy to see that the assumptions A1 and A2 are fulfilled. So our main result is the following. Yeah, that it is possible to generate the whole set of efficient elements of a constraint optimization problem by solving two unconstrained optimization problems, one with the original objective function and one with a penalized objective function. Yeah? Because under this additional assumption that F is component-wise semi-strictly quasi-convex, we have here the equality. And I would like to show you the proof of this assertion. At first, we start with elements belonging to this union here, and we have to show that we have an element belonging to the set of Pareto-efficient elements of the constraint problem. Yeah, from corollary 4, we know that this inclusion is true, and so we consider elements x0 belonging to this intersection. Then we can use lemma 3 and our assumptions for deriving the result. Here you can see this is the assumption A1, this is the assumption A2 that we are using, and here this inclusion follows from lemma 3. And then we have this condition such that we get, again, from lemma 3 that x0 is a Pareto-efficient element of the constraint optimization problem. So in the other direction, we start with an element belonging to the set of Pareto-efficient elements of the constraint problem. Yeah, we have two cases here. In the first case, we finished our assertion. And in the second case, we consider x0 belonging to this set here. And using our results mentioned before, we can assume that x0 belongs to the boundary of x. And again, using lemma 3, this is lemma 3 here, and the assumption A1, this is this one here, we get this inclusion. Furthermore, we have to show that this equality in 1 is true, and for this it is sufficient to show that this intersection here is empty. If we consider an element x1 belonging to the interior of x and x1 belonging to this set, then we arrive in each case at a contradiction. So this means that the equation 1 is true, and taking into account that x0 belongs to the boundary of x and A2, we get this relation here, such that we get together with this inclusion here and the formula 1, and furthermore lemma 3, that x0 belongs to the set of efficient elements of the unconstrained problem with the penalized objective function. And so our proof is finished. So, concerning some applications, I would like to mention the example from the beginning. Here we consider a multi-objective location problem where the Euclidean norm is involved, and this was the problem. Here, under convexity assumptions concerning x, however, our results are true without assuming convexity of x. However, to show that we get here the same results like in the paper by Nguyen and Michelot, you can see here our solution method. We compute the set of Pareto-efficient solutions of two unconstrained problems, one with the original objective function and one with a penalized objective function. And then we have to compute here the intersection of this green Z with X, this is this one, and the intersection of this blue Z with the boundary of X, such that we get this these elements here in blue color. And the whole solution set of the problem is to see in green color. And this is not surprising because we get the same solution set using the results by Nguyen and Michelot. This should be the case, of course. However, our results are also true without convexity assumptions concerning X. We consider location problem with forbidden regions. The forbidden regions are introduced here by X. We consider such sets Xi and the feasible set X. So, and these are examples. In red color, you can see the forbidden regions, and outside of the red regions is the feasible set. So, and then we introduce two penalized functions. Here we have the penalization functions. This is this one. Yeah, and using the notions by Urani, Michelot, and Nguyen, we can speak about location problems involving attraction and repulsion points with this additionally objective function. And Christian Günther derived this nice result here concerning the solution set of the constraint location problem, where in the description again, the set of Pareto-efficient solutions of an unconstrained multi-objective problem with the penalized objective functions that you can see here is involved. And here in this figure, you can see the procedure. We have to compute these set of efficient elements, and then we have to generate the corresponding intersections. And so in green color, you can see the whole solution set of this location problem with forbidden regions that we can solve using our methods. So in the last part of my talk, I will speak about necessary optimality conditions, where we are using our results from section 4. We will use an axiomatic approach to the subdifferential. We consider an operator associated with functional H, and we suppose H1, H2 is H3. In the case of a convex function H, then this operator coincides with the subdifferential in the sense of convex analysis. Furthermore, under locally Lipschitz conditions, and in the case that X bar is a local minimum of H over Rn, we have this necessary optimality condition. And furthermore, we have here a chain rule that we need for deriving our optimality conditions. Yeah, and here you can see the theorem where we apply our results from section 4 under the assumption concerning the subdifferential and our standing assumptions A1 and A2. Then we have component-wise semi-strictly quasi-convex for the vector-valued function, and we consider a weakly Pareto-efficient element of the constraint multi-objective problem. And we suppose some Lipschitz condition at X bar, and then we get for X bar belonging to the interior of the feasible set that this necessary condition is fulfilled, and furthermore, if X bar belongs to the boundary of X, we have this necessary optimality condition. And as you can see in our formula, no normal cones are involved because we derive the whole set of Pareto efficient elements here by computing two solution sets of unconstrained problems. Yeah, so no normal cones are involved here. So, and finally, we apply our results to approximation problems involving non-convex constraints in order to formulate the multi-objective problem with an objective function where the vector-valued norm is involved. Yeah, we define this vector-valued norm here for the case that we have a classical norm. Then you can see that the axioms of a norm are fulfilled here for this special case. So, and this is our multi-objective approximation problem, where the vector-valued norm is involved. We have additionally a function g from A to the m-dimensional Euclidean space, and we suppose it is component-wise convex and continuous. Yeah, the feasible set is not supposed to be convex but closed. So, and so we have this objective function. And for the optimality condition, we need additionally a rule for sums for the subdifferential, for the axiomatic subdifferentials. This is H4. So, and under these assumptions here, standing assumptions A1, A2, and these are the assumptions concerning the axiomatic subdifferential, we consider a weakly Pareto efficient element of the constraint approximation problem. This is Lipschitz condition concerning the penalization function. Yeah, and then we get this necessary optimality condition for the case that x bar belongs to the interior of the feasible set, and this is the case that x bar belongs to the boundary of the feasible set. And here is set d of x bar involved, and here you can see nothing else than the structure of the subdifferential of the vector-valued norm. And if we would consider the scalar case, the classical norm, then you can see here the conditions for elements belonging to the subdifferential of the norm that one can derive using Hahn-Banach's theorem. Yeah, and for elements belonging to the boundary of omega, here we have additionally a component S star such that this necessary optimality condition is fulfilled. Yeah, and here you can see again, no normal cones are involved in the assertions. So, some conclusions: we will apply our results for other types of location problems, and also in bioinformatics, we considered their entropy problems that can be formulated as approximation problems, and so hopefully we will derive necessary optimality conditions and corresponding solution procedures using our results that I presented here. Here are several references. These are some papers where penalization methods are involved. Yeah, this is one of our papers. Yeah, Hirayuti function was mentioned in the talk. Yeah, this famous book by Alex Joffe, Johannes Jahn, the book on vector optimization. Yeah, this was the example for location problems where the Euclidean norm is involved. Yeah, we are using results by Nikolai Popovich concerning generalized convexity, and also these results. Yeah, and also the book by Konstantin Salinescu. So, and now we would like to invite you to visit our software flows. This means facility location optimizer, and in the software many methods for solving location problems are involved. In this figure you can see a screenshot of this software flow, and here it is an example for a location problem. The existing facilities are in red color to see here. These are the existing facilities in a town. This is a map of the town Halle, and the solution set of the multi-objective location problem involving the maximum norm is this set in blue color. And if you would choose the Manhattan norm, then you would get such a solution that you can see here in green color. So that's all. Thank you very much for your attention.
Thank you, Christiane, for your talk. Is there any question to our speaker? So you can just unmute yourself and then ask question.
Hello, Christiane. Joy.
Hello.
We will start the video.
Yeah.
Hello, Christiane.
Joydeep.
When you are doing this numerical implementation, what are the algorithms you are using? You have this beautiful, but
yeah, especially here for these multi-objective location problems, we are using an algorithm based on duality theory. Using our duality statements, these are Lagrange duality statements, we can derive a very simple geometric algorithm for generating the whole set of efficient elements of these location problems. And this is involved in the software flow that you can visit here with this website. And it is free. It would be very nice if you could visit this website.
Because I was thinking of using a kind of gap function type thing, which I had also done for a location problem.
Yes, this would be also a possibility. However, we were using duality statements.
Okay, that I'll go and look at it surely. Thank you, Christiane. It was a very nice talk. Very interesting results.
Yeah, thank you.
Yeah, thank you, Christiane, for your talk. Is there any other questions from the audience? We can quickly, so please join me to thank Christiane.